So now that we've defined simple harmonic motion, let's now talk about the energy that's associated with a system that is engaging in simple harmonic motion. Now, I will put the qualification that as long as our system is frictionless, which we largely that will always be true in AP Physics 1, but you should always read the problem and ensure that yes, the system is frictionless. But as long as that is true, simple harmonic motion should abide by conservation of energy. And there are two different types of energy that are present when we think about this oscillating motion. One of them we talked about regularly in the previous lecture is kinetic energy, right? Because we talked about motion a whole bunch and when our is our system, at rest? When is our system moving really fast? So that's really an evaluation of what's going on with the kinetic energy in our system. And the other kind of energy that we see kind of depends on whether or not we're looking at a pendulum or if we are looking at a mass spring system. Because when we stop, so I'm going to take this horizontal mass spring system as my example here. When my box moves perhaps to the right and eventually comes to a stop, we know that we will no longer have any kind of kinetic energy, but since our energy is conserved, it must have become something else. And in this case, the energy went into stretching the spring. So by the time we get out here, right, this is all going to be spring energy. And that's true in a vertical mass spring system as well, that there will be some spring energy. With a pendulum, though, there's no spring here. So instead, we got to think about what's going on perhaps at the lowest point in the swing of the pendulum. And the fact that when we stop moving, we are higher than that lowest point. And so we end up having gravitational energy at this location and this location. Now, both gravitational energy and spring energy are categorized as potential energies. So we will say that during the oscillation of an object undergoing simple harmonic motion, we will see some combination of kinetic and potential energy in the system. Let me just add this note that potential could be gravitational or spring. All right. Fantastic. So what I'm going to do is I want to talk about each of those specifically, and I want to talk about what kind of patterns we can see in both the kinetic energy of our system and then in the potential energy of our system. And I'm going to look at a pendulum. So I'm going to really quickly draw a pendulum here. And I also want to talk about a horizontal mass spring system, right? We want to be able to identify patterns in both of these. So what we want to do is we're going to want to look at the extremes of each of these. So not only do I want to draw my pendulum when I've pulled it back, I also want to draw the pendulum right when it is swinging through its lowest point. And then I'm also going to try to draw this pendulum when it rises to its highest point on the other side. And correspondingly, for a mass spring system, that means that I have, this is going to be a little bit harder to illustrate, but we're going to say that I pulled my spring to the right, or my mass to the right. It goes through the equilibrium position, and then it compresses the spring as it moves to the left, okay? So if I was going to perhaps number these, it would be 1, 1, 2, 2, and 3, 3. Okay, so position 1, position 2, position 3. Oh, and let me add the equilibrium point, because that's always a good reference point for us to have, right? So this is equilibrium for a pendulum, and this is going to be our equilibrium for our horizontal mass spring system. Okay, fantastic. So let's look at all of these extremes and kind of detail what is going on with our motion. When we first pull a pendulum back, we pull it away from our equilibrium position and we hold it at rest. So the velocity is 0 when we are at that extreme. And that is true in our mass spring system as well, right? When we stretch our spring, we are going to pull it away from the equilibrium position and we are going to hold it at rest. Now, once this is released and is allowed to move, it will move back through that equilibrium position. And this is where we are going to see the max velocity, right? This is where it's going to move as fast as it ever does, because we've had this restoring force pulling towards the equilibrium position, causing our object to speed up. So we would expect to see our maximum velocity at that location. Now, as soon as we move through equilibrium, right? So now that we are heading from position 2, from position 3, our restoring force is going to be pulling us in the opposite direction of our motion. And so we're going to expect to see that we start to slow down. And by the time we reach this extreme, on the other side of our motion, we have returned to a velocity of 0. Okay, so this pendulum, once it reaches right here, it stops, and then it's going to start to swing back towards equilibrium, excuse me. For our mass spring system, we're going to compress the spring until the mass stops, and then the spring is going to push that mass back towards equilibrium. Okay. Now, what does all of this mean? All of these different velocities or speeds. I guess we can just go for speed right now. What does that mean when we think about what's going on with the kinetic energy? So let's do a quick graph to help us visualize this. We're going to put kinetic energy on our y-axis. And we're going to graph it as a function of time. So as time goes on and as we oscillate and go back and forth and back and forth and back and forth, what does this speeding up and slowing down really make our kinetic energy look like? So starting with that pull to position 1, at position 1, right, we are not moving, and thus we would expect that there is no kinetic energy. But then we speed up until we get to some kind of maximum, right? We are going to, starting at position 1, by the time we end up getting and passing through position 2, our kinetic energy is going to go up, 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 up. And as soon as we pass through position 2, it's going to go back down, 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 down. Why is it going back down as we head towards position 3? Well, that is because at position 3, we stop moving yet again. So our kinetic energy has to go back to 0 by the time we are located at position 3. And then we swing back, right? So we're going to swing back towards position 2. So we increase our speed. So we would increase our kinetic energy as we swing back towards position 2. But as soon as we go through position 2, it goes back down again to 0, because at this time we have returned back to our original location. We are returning back to position 1. So you can see that this is creating for us a kind of sinusoidal relationship or function, right? It's that kind of like up, down, repeating pattern that goes on forever. And we're going from a kinetic energy of 0, right? That's either extreme, and we increase up to our equilibrium position. The equilibrium position is where we are achieving our maximum kinetic energy. Now let's do the same thing, but let's now think about it from the perspective of potential energy. So what I'm going to do is I'm actually going to copy this entire thing because I don't want to waste your time. Ooh, redrawing it, and we're going to end up drawing a very similar situation. So looking at the same um, pendulum and the same horizontal mass spring system, let's now take a look at what those two systems look like from the perspective of potential energy. Now you have to remember, potential energy is going to include both gravitational and kinetic. Or sorry, whoa, gravitational and spring. I was on autopilot there. Okay, so in the case of a pendulum, we're really thinking about what is going on with the change in height from our lowest point. So there is the bottom of our swing. So this is our lowest point, right? So this is a delta y of 0. And our maximum delta y is going to occur at the extremes. So position 1 and position 3. Okay, and this is really the opposite of what we saw with kinetic energy. Kinetic energy, we saw that at the extremes, right, our velocity was 0. Now at the extremes, our height is maximized. So we're maximizing potential energy at the extremes. We are minimizing our potential energy by going through the middle, which again is the opposite of what we saw for kinetic energy. So that's something that's interesting we should keep in mind. And we actually do see that same pattern when it comes to a horizontal mass spring system, okay? So for this system, we are moving to the right, perhaps some kind of positive displacement, or we are moving to the left, some kind of negative displacement, right, away from our equilibrium position. But in either case, whether we are moving to the right or we are moving to the left, we really are maximizing the stretch in our spring. And we have minimized and in fact zeroed the stretch in our spring when we are at that equilibrium position. So it's the same pattern, right? We're seeing that our potential energy is going to be maximized when we're at our extremes, and our potential energy is going to be minimized when we are at our equilibrium position. So when we try to show that on a graph of potential energy, we're going to start, right, by starting at position 1, we're going to start with a maximized potential energy. And from position 1 moving towards position 2, we're only going to see it fall because we minimize our potential energy by the time we get to position 2. And then as we go to the other side of our equilibrium position, we increase our potential energy back to its maximum. So by the time we get to position 3, that's been maximized again. And then we turn around, come back to position 2, go through the equilibrium position, and return again to our starting point of position 1. So we are seeing another sinusoidal style of function, but where it begins is different from kinetic energy. Kinetic energy, we started with a minimum. Potential energy, we're starting with a maximum. And then every time we reach a minimum, we see that the other function reaches a maximum. Okay, so we've got this kind of opposing minimum maximum action going on. And so if we decide that we want to try to show both of these on the same graph, so we're going to create one last graph here. And this is going to be a graph of total energy as a function of time. What we see when we do this is that, we're going to have our kinetic energy, we're going to have our gravitational energy, or sorry, potential energy. And we now can more clearly see the fact that when one is maximized, the other is minimized. So this would be position 1, position 2, position 3, back to position 2, back to position 1, etc., etc. And if we add these two things together, right? So if we add that kinetic energy and we add that potential energy, which by the way, that's what this was potential energy. If we add those two together, we end up getting a consistent amount of total energy, which agrees with what we said at the beginning of this portion of the lecture, that as long as our system is frictionless, we should abide by conservation of energy. The total amount of energy in our system should be consistent throughout time.